Hey guys, I want to take a few moments to talk about the concept of torn pages. Not really a concept, it's actually a problem in database systems that people need to deal with. Pretty much all database systems need to deal with. And that problem occurred because of this like 700 layers between us and the backend, the database, right? And then the file system, the operating system page cache, and finally the SSD or the hard drive. There's like so many layers between them. And the problem happens in between this. And it all comes down to the concept of a page, which we talk about a lot, right? The databases only deals with pages for simplicity. It doesn't matter what you have, rows, columns, graphs, databases, vectors, whatever, documents, whatever you want, eventually end up as a page, you know, with the content. And the page, the databases use fixed size pages. And the page is nothing but an abstraction. You see, it's a collection of bytes. It has headers that tells you what's the content, what's in this page, the size, whatever, and then the content itself. And pages are often, almost always, fixed size for simplicity, right? So if I have, Postgres uses 8K pages, Mongo, I believe, uses 32, at least for the leaf nodes in Wire Tigered. And Anno uses 16. So you see there is different fixed size pages. And that applies for both indexes, actual tables, the whole 9 yards. Walls are slightly different, the wall entries. I'm not going to go into that. But that's what we have. We have a page, right? So the page has a fixed size and has a headers and it has a content, right? So I say 8K. But you see, there is when the database tells the OS, hey, write this 8K on this file from this position, write 8 kilobyte, and this is the 8 kilobyte. You see, there's no fixed size bytes like that in the OS. You see, because we're dealing with the OS. And the OS uses file systems. Now that you can, if you want, skip the file systems with ODirect, but let's not talk about that. Mostly we're built on top of the file system, which uses files and directories, which are really, if you think about it, are built for end users. Really, databases don't need files, if you think about it, or directories. But we do use files as just a logical ways to group things. We can use a simpler way to group. But files, it comes with files that were designed as a, for end users mostly, as far as I know at least. So file systems also uses concepts similar to pages, but they call it blocks. Okay? So there are fixed size block, and it's called the file system block. Now, I'm going to skip the OS page for now. We can talk about it in another video. But this block in the file system often is set to 4 kilobyte. It cannot exceed it. Why? This is another whole discussion with the fight between the file system guys, the storage guys, and the operating system guys. Nobody talks to each other. And the limitation is because of the operating system page cache, which is set as 4 kilobytes, so that you cannot exceed it because of certain, simplicity and complexity that goes into it. But for now, the block size, 4K. You cannot go more than 4K. Well, this raises a problem because my page is 8 kilobyte or 16 kilobyte. I told you to write 4 kilobyte. What does that mean? Right? I told you to write 8 kilobyte. What does that mean? That translates 1 8K is 2 file system blocks. Well, to the OS, the OS have no idea that those two has to come together. You asked it to write 8 kilobyte, and it doesn't even, the OS doesn't know that this is a page, right? A database page. It knows this is a bunch of bytes. That's all you're writing. Right? So you're writing, it will translate this into 2 file system blocks, so 2 4 kilobytes. Cool. All right. So it will say, hey, write this 4K, write this 4K. What does that mean? That 4K will be sent as a command to whatever the device controller, right, on the storage controller. It says, hey, write this LBA and this LBA, because we're dealing with logical blocks at the end of the day. So block number 7 and 8. The disk will receive the command for 7 and 8, right? And then it will say, hey, I received that command, but for any reason, I only wrote the first one. The second block, sorry, the OS crashed, the disk crashed, any other reason, right? So somehow the disk control didn't get the message that the second block was written, right? Was about to be written or asked to be written. Because to the OS, it treats everything as atomic blocks. This block is atomic. I'm going to write this whole unit for you, and I'm going to make sure it's atomic. Even the storage size will treat this as an atomic operation. That 4K, I'm going to write it atomically. It goes, if half of that fails, I'm going to roll it out. But if it writes, it's good. But this causes a problem. But now it's possible that half the database page gets written and half gets failed. If an OS crash, power failure, and the disk did not get the second message that, oh, you want this other 4K as well. So this causes a problem. And this is called a torn page, where you essentially wrote the first half, but the second half didn't get written to disk. Of course, this is a corruption, right, in database, because now you've written something and the other thing doesn't match it. So we can, in database system, we can detect this easily, right? On the database crash or the OS crash, when we come back, we read the page and we say, oops, this page is bad. How do I know? Well, checksum, right? If I written the first half, I'm gonna write the checksum for the content, because the checksum and the content were in memory at some point. And as we written the checksum, but when we read it and we do the checksum, it's like, oh, something's bad. That doesn't look like it matches, so we flag an error. Now, it's up to you. What do you want to do? So you got a torn page. What do you do? How do you solve it? Well, I'm going to talk about the simplest way to solve it, which Oracle does. Oracle on the background has, I forgot what it's called, something recovery manager. It just takes the physical pages and just writes them in a backup area. Just, it's asynchronous, and does that. Just backup. As you continue writing, if you have if I know if there is a page on this that is good, I'm going to read it and just flush it to somewhere else. Back it up. So we'll start backing up all the pages, right? And of course, it will renew this and it will overwrite this. So yes, more work, but eventually if we detect a bad page on recovery, a torn page or a partial page as they call it, then we can recover from a good page. So that's one way to solve it. That's how Oracle does it. InnoDB, MySQL, solves it by doing double writes. So every time you write something, instead of writing directly to the OS, if we want to write a page, we never write to the OS directly. We write it in something called the double write buffer. Let's write it in this area first. And if it's successful, eventually save that in the double write buffer. It's another file on disk, and we can write to it, right? So now if in case while writing to the OS, that page got torn, the OS crashed or anything, the restart will detect the page because of the checksum, and we know that every page eventually is going to have a matching double write buffer page. So we look it up and we restore it from the double write buffer. So this is actually slower in MySQL if you think about it, because your write is actually doing multiple IOs, right? You're doing a write here and another write to the actual, shared buffer or eventually the OS, right? But MySQL team says, no. Actually, it's actually less, because you see, it's not random writes. See, double write buffer is, because it's a creation of our own, I can write it in sequence. And if it's sequential, it's a beautiful, fast I/O, because disk live sequencer stuff. If you write, hey, I want to write this X number of LBAs, they love it. But if you tell it like, oh, write in this LBA and then write in there and write in there, you need to do issuing multiple commands, right? It comes down to the commands at the storage level, and that's the problem. See, so that's how MySQL solves it. You can disable that if you want, like in testing environment. You don't care about integrity, just disable the double write buffer. One problem that I had understanding with the double write buffer, MySQL, is like, wait a minute, you're writing twice. Well, you can have you still have the same problem in the first case, right? Because you can get a torn page while writing to the double write buffer. I was like, what's the point? Then I thought, and of course nobody talks about this, right? Until I actually think it through. It's like, oh, yeah, of course. Let it be corrupted. That's fine. It's just the double write buffer. The original page still lives in the original InnoDB files, right? We wrote it to the double write, and when we crashed, hey, we just have a bad double write buffer. We're gonna discard it, and we can restore it from the wall. And we have the original copy in the original file. Remember, because we are writing twice. So if we fail the first time, fine. If we didn't fail, that means we have a good write in the double write. And the second one, we have essentially, we might fail in this writing to the OS files, the normal files, and then we might get a problem. Okay, and then we can always restore to those. And finally, Postgres has something called the full page write. If you enable that, right after a good checkpoint, right, it will store the value in the wall, right? It stores the full copy of the page in the wall. So in case of a partial failure somewhere after that, we can always have a good copy of every page from the wall, from the write-ahead log, which is impressive. I like that solution better, if you ask me, right? A little bit blows the wall, but yeah, the price to pay. So yeah, I love this topic, and I'm exploring this more and more, and I'm finding so much other stuff in my exploration and research. Like I just discovered something called the NAND page. Well, I know about the SSD NAND page before, but I didn't know that is actually different than what we deem the physical sector size, which is also different from the logical sector size, which is the LBA essentially. Right? So those storage guys are doing their own thing in order to save on the DRAM in the storage by making the pages higher, just for the FTL, the flash translation layer. So they have less entries, they make the pages bigger, but it also causes other problems that I'm reading about right now. Yeah, that's about it, guys. I wanted to talk about that. See you in the next one.